Good afternoon. My name is Andrea Avanzini from the University of Brescia, Italy, and today I'm presenting a research on numerical, mechanical, and metallurgical analysis of an innovative lightweight titanium con rod additively manufactured. This research is being carried out in cooperation with the Italian company Strupperava, which is based in Brescia as well, and with Norwegian University NTNU. The general background of this research is that car manufacturers and their suppliers are facing new stringent legislations for the reduction of air pollution from transport. And to achieve this goal, weight reduction of vehicles is obviously very important since it directly brings to a reduction of fuel consumption and emissions as well, with the additional advantage of increasing vehicle efficiency and performances. In this context, the additive manufacturing technologies may be particularly useful since they allow to follow the principle of using material only where it is needed. And in particular, they make it possible to print very complex shapes, such as those that can be generated with topology optimization or generative design. There are, of course, some issues to be considered, and for example, the dependency of mechanical properties on the specific process and heat treatment. Also the fact that the knowledge of fatigue properties of AM material is still incomplete, especially when it comes to full-scale parts. And finally, there's a need to integrate the design for fatigue inside the topology optimization approach. So today I'm presenting a case study which deals with a connecting rod or con rod, which is a very critical engine component. It is usually made of forged steel, but for some niche application also titanium forging is applied. And actually the case study that I'm presenting deals with the substitution of a conventional forged design with a new solution obtained after topology optimization, consisting of a near net shape design in titanium alloy manufactured with SLM technology. And what you see here is a sort of multi-branch structure that was obtained in an early phase of the research by topology optimization that was carried out by the company. And this solution has several potential benefits, and one of these advantages is weight reduction, which could be quite significant in comparison with forged solution. But also some advantages are related to meshing operation, which are easier because it is possible to manufacture the connecting rod into two separate parts. And there's also the possibility to integrate cooling channels inside the con rod. The next phase of the research, after printing some prototypes and samples, was material characterization and heat treatment selection. So this activity was carried out by our colleagues from Metallurgical, and in particular they compared different types of heat treatment, both at low and high temperature, and they considered different building direction and carried out tensile tests, XRD analysis for residual stresses, micro hardness, corrosion test, and in the end they selected a super beta transverse sublimation followed by tempering as the most promising heat treatment among those analyzed. And here we can see a comparison of the stress strain curve of the heat treated SLM material in comparison with the forged equivalent alloy. In parallel, they also carried out metallurgical analysis on the microstructure, and the main findings were that the effect of the heat treatment was to induce isotropy of the microstructure, and in general, the transformation into alpha plus beta structure inside prior beta grains. So these investigations were initially carried out on the spaceman, but they were then repeated on selected sections of the full-scale con rod, and in general the same type of microstructure was observed. Now, having available a few prototypes, some fatigue testing were then carried out, and in particular, these were carried out in the laboratories of NTNU, and the conrod prototypes were subjected to axial loads under tension and compression. The loads were transferred to the conrod using pins, and with this configuration, and due to the high compression loads that are expected, a custom fixture that was available in the laboratory was used to properly connect the parts to the test machine. And here you can see an intermediate phase of the mounting. In this picture, you can see instead the actual conrod before the test, and in this picture you can also note the presence of a lubrication system that was used to lubricate the contact surfaces of the loading pins and the bearing holes of the conrod. In this next picture, you can see the actual shape of the conrod after heat treatment and after blasting with ceramic beads. In terms of results, we carried out tests with a target life of 2 million cycles, a load ratio of R equal to minus 2.66. A total of 7 fatigue tests was carried out within 4 different load ranges. And the first result is that for the higher load level, a reduction of fatigue strength of this new solution was observed in comparison with the conventional conrod. By lowering the load level, we were able to obtain a first full-scale conrod life curve, and in particular to gain our first estimate of the load level that may correspond to infinite life. In parallel with fatigue testing, we also implemented a finite element model of the fatigue test, and in this model, a very important aspect is the inclusion of the contact interaction between the conrod and the pins that were modeled as analytical rigid surfaces. Because as a consequence of this interaction, what happens is that when switching from tensile to compression load phases, there is a change in the distribution of contact pressure, and as a consequence, there is a different stress flow within the branches of the conrod, so the contour maps in the two phases are quite different. In general, the stress values remained well below the static strength, but at the moment, it is not yet possible to make a comparison with fatigue strength data, since these were not yet available. Nevertheless, the finite element model allowed the identification of potentially critical locations, especially in the outer strats and at the connection between the big N and the central region. So in this area, we carried out more detailed analysis. Considering the results of fatigue tests, what is interesting is that there is a good agreement between the numerical prediction and experimental findings in terms of location of the failure, which mainly occurred in this area at the base of the connection between the central region of the conrod and the big end. The failure initiation was identified on the fracture surfaces, and a parallel fatigue crack growth on both sides of the conrod was observed. In this area, some investigation on the presence of defects was also carried out. So a few defects were found in limited areas of the component surface, not far from the fracture surface, although in general the quality of the conrod was very, very good. So the conclusion is that the interaction between stress concentration in this area and the presence of some surface defects induced by the SLM process actually may explain the failure of the. So in conclusion, at this stage of the research, we have obtained our first fatigue life diagram of the full-scale components, which is quite an important result. And we have a finite element model that is in good agreement with numerical analysis, so we hope in the future to use this model to better evaluate the effects of the notches that are generated by the particular geometry of the conduit. And finally, of course, fatigue test data on AM titanium samples are needed with a selected heat treatment. They are not yet available, but the tests are scheduled very soon. And with this data, we will be able to use a proper fatigue limit in the design of the column, and hopefully to calibrate local fatigue prediction criteria, such as the theory of critical distances and strain energy density. And in the end, we would like to include fatigue evaluation in the topology optimization loop. So thank you for your attention.